In our final video in this series, we're going to look at the sequence of chemical reactions that leads to the production of ionic bases, such as sodium hydroxide, that we'll see in this first reaction here. Now, in order to do this, this process actually requires two steps, the first of which being a relatively simple single displacement reaction that occurs whenever a pure metal is dropped within water. Now, even though water is not an ionic compound, because metals exclusively lose electrons when they ionize, sodium, upon being dropped in water, is going to lose its valence electron, therefore becoming Na+, allowing it to displace the hydrogen in water and form the ionic compound sodium oxide, thereby liberating hydrogen from water and producing hydrogen gas. And if this reaction were to take place underwater, you would actually see bubbles forming, which would actually indicate the hydrogen gas that is being produced. And of course, we can balance this reaction by adding a coefficient of 2 to balance out sodium. So this represents the first stage in the production of a base, and we don't actually have a base yet. Instead, we have this compound here, which is an ionic compound that can more specifically be classified as a metal oxide ionic compound, in this case, sodium oxide. Now, sodium oxide is actually really unstable because the oxygen ion actually has a -2 charge that immediately wants to undergo a second reaction with water, and that's exactly what we see, or rather you wouldn't see it, because sodium oxide only lasts for an amount of time that is less than a second, and then this will actually undergo a synthesis reaction with the water inside of the solution in which it was made. And if we do a synthesis reaction, if we treat sodium oxide as our A and water as our B, we can actually get the base sodium hydroxide as the product from this reaction here. And we can balance this instantly by putting a balancing coefficient of 2 so that we see that both sides contain 2 sodiums, both sides contain 2 oxygens on the reactant side, one from sodium oxide and one from water, and 2 hydrogens, both of which from water like this. And this is the process that leads to the production of bases, and all that you need to do is add a metal, preferably a reactive one, to water in order to get this reaction here. And if we want to write the overall reaction, we do the same thing that we did with any compound reaction. Any compound that is the product in one reaction and then subsequently appears as a reactant in the next reaction, this means that this compound is consumed and therefore it no longer appears in the final equation, and therefore our overall reaction would simply be sodium reacting with water in order to produce our base, sodium hydroxide, and of course we would get hydrogen gas that is liberated from the single displacement reaction in the first step. And from here, all that we would need to do is balance out water and sodium in order to have our balanced chemical reaction. Now, chemistry teachers enjoy demonstrating these reactions, particularly with violently reactive alkali metals such as sodium, potassium, or any of the ones below it if you have the safety equipment for it. Now, these reactions tend to produce very noticeable explosions during the reaction, but it's not actually the alkali metal that is exploding. That basically just disappears and then turns into the base, which is fully soluble in water. What actually explodes is the hydrogen gas as it reacts with oxygen, because most of these reactions also release a significant amount of heat, which is able to ignite the hydrogen gas in oxygen and cause it to burn, producing water in a separate reaction entirely. And sodium is actually one of the more tame examples of this type of reaction. For a more entertaining reaction to watch, you can watch what happens when potassium is reacted with water, which not only reacts faster than sodium, but produces a very characteristic bright pinkish white flame when the hydrogen ignites in the reaction. But the actual breakdown of the reaction remains almost identical. Potassium undergoes a single displacement reaction with water, and because potassium as a metal loses its valence electron, it would form a cation, therefore displacing hydrogen from water, giving us the metal oxide, potassium oxide like this, and liberating hydrogen, which would then ignite and produce this characteristic bright pink flame when it is liberated from potassium. Now, as with every metal oxide, potassium oxide is very, very unstable, and this ionic compound, specifically the oxygen ion, will undergo a subsequent synthesis reaction with water that we'll see in the next step. So if we take our potassium oxide from the first step and undergo a synthesis reaction with water, we would get the base potassium hydroxide like this. And we can balance this reaction simply by adding a coefficient of 2 here, and we can do that for the first step as well. And since potassium oxide is a product in the first step and then consumed immediately in the second step here, it would not appear in the overall reaction. Instead, all that we would have would be potassium hydroxide, the base that we produce, and the hydrogen gas produced in the single displacement reaction, which would pretty much immediately ignite from all of the heat that was produced by this reaction. And all we would need to do is add balancing coefficients of 2 to both potassium and to water in order for our equation to be fully balanced. And more or less every synthesis of an ionic base reaction would work more or less identically to this. Therefore, to test your knowledge on these formation reactions that are used to produce metal hydroxides, i.e. Ionic bases, you can take a look at the sample reactions below and see if you can complete the single displacement and synthesis reactions and use them to derive the overall reaction that results in the production of a metal hydroxide base.